All right, so today we are going to be looking at factors that influence the radiosensitivity of an organism. And so this is a follow-up to biological interactions. We know that when we send a beam of radiation into our patient, the patient's body or the atoms and molecules of that patient's body are impacted by the radiation and energy is transferred. That energy that's transferred can cause biological effects. How is the energy transferred? Well, it may be transferred either directly or indirectly. That we talked about that last class. So direct action, where the photon ionizes a target molecule, which our typical target molecule is DNA, but there could be other identified important molecules such as the RNA, things like that. Or energy can be transferred indirectly, where the initial ionization occurs on some other molecule, typically water. The water's ionized. Ionized water is not stable, so it dissociates, it breaks up. And when ionized water dissociates, it breaks up into free radicals. Free radicals are molecules that have excess energy. They are frenzied. They can move short distances through a biological system, and they interact with and ionize and excite everything around them.
Miss Dawn.
Yes.
All we see is your beginning slide. Is that what we're supposed to see?
That's what you're supposed to see. I've not gone any further. Okay.
When they break apart, when you say a hydroxyl, how does it look? Because I got a little confused. I know that that is going to be an O and an H, right?
Yes, a hydroxyl is an O and an H. If it's an ion, it will either have a OH negative if it's a negatively charged hydroxyl, or it will have an OH with a positive or a plus sign if it's a positively charged hydroxyl. If it's a hydroxyl free radical, it will have an O and an H and then like an asterisk afterward. Okay, but they're all hydroxyls. The O and the H is a hydroxyl. It's just if it's an ion, it either will have a negative or a positive sign. If it is a free radical, it has the asterisk. Okay, just like the hydrogen, if it's positive, if it's an ion, it will be positive or negative, and if it is a free radical, it will have an asterisk behind it. Okay, so with the free radicals, like I said, the free radicals can move through, they can transfer energy to the target molecule. Now, the interactions that are done either directly or indirectly in the diagnostic energy range are photoelectric and Compton. So those are the interactions at the atomic and molecular level that are ionizing the atom. Now we know 80% of the time the energy creates ionizations. 20% of the time it creates excitations. So all of this is information that we've covered in last week's class. So like I said, today we're going to look at these not specifically interactions, but things that influence the radiosensitivity of an organism, so they help determine how much damage will occur in that organism. So these factors that influence the biological effects of radiation are divided into two categories. I divide them into what I call biological factors that are related to the organism and physical factors that are related to the radiation. What kind of radiation would a person be exposed to? How quickly was it delivered? Was it spread out over time? So all of those things related to the radiation fall under physical factors. So we're going to start first with biological factors. And before we do that, I want to give you some page numbers in your textbook for reading. I hope they are on the syllabus and they're correct. But in the Carroll text, it's chapter 41, pages 753 through 757. And that's talking generally about cellular effects on radiation and cellular response to radiation. And we'll also come back to that in the next unit. Then it's also pages 765 through 771. So that's in your Carroll text. In the radiation safety, your radiation safety book, this is in chapter 7, and it starts on page 116 and goes to page 120. So just a few pages there.
You said it was what, 60 to 120?
It's 116 to 120, yes. And that's the Statkowitz-Shear textbook.
You said chapter 7.
Yes, chapter 7. And in the Carroll text, it's chapter 41. Okay, so we're going to start by looking at biological factors. So things about the organism that we are irradiating. So we're going to look first at tissue sensitivity. Then we'll talk about the effect of oxygen on radiosensitivity. We'll look at age, gender, temperature/metabolic rate, stress level, and body weight. So we're going to look at all of these different factors and how they influence the damage of radiation on an organism. So we'll start first with tissue radiosensitivity. And tissue radiosensitivity was first described by two French scientists. And I just usually call it the law of B and T because I don't speak French. I did have a student who spoke French fluently, and this is my best guess. I think it's Bergenet and Tribondeau. But for me, typically it's the law of B and T.
Hey, that sounded legit to me, Dawn.
Huh? Sounded good to you? Well, good. My French is probably extremely rusty. I don't think I've had it since 9th grade, which was a long, long time ago.
Sounded very French to me.
What B and T said was that cells that are poorly differentiated and rapidly dividing are the most radiosensitive, and cells that are highly differentiated and slowly dividing are the most radioresistant. So let's look at this. What does it mean, poorly differentiated and highly differentiated? Y'all had the pathology class in the summer, right?
Yeah.
Okay, so that was one of the things that y'all talked about was cell differentiation. So what does that mean? Any ideas? What's the difference between poorly differentiated and highly differentiated cells?
Differentiated is when the cells have a function or they're like a specific type of tissue or cell. And poorly differentiated is when they're like stem cells, basically.
Okay, wonderful. That's it. That is exactly correct. Cells that are poorly differentiated are very simple. Okay, so they don't have a specific function yet. They might also be called precursor cells, Yeah, precursor cells, stem cells, or poorly differentiated cells. They are just very simple. And most of the time, these cells are designed to replenish a cell population. So they are rapidly dividing.
Don, did you say stem cells and
Stem
precursor
cells, yes. They can be called poorly differentiated stem cells or precursor cells. Okay, either of those three terms might be used. But those cells, if you had them, plated in different petri dishes and you irradiated them, they would be pretty easily killed because they are simple and they can't handle much radiation exposure. Now, if you look on the other end, the highly differentiated cells, Ivy had it exactly right. Highly differentiated cells are very complex. They are functioning cells. They're what's doing the work of whatever tissue or organ you're talking about. Functional cells don't divide, or they divide very slowly. So those cells can withstand a lot more radiation before they would experience damage. Therefore, they are considered radioresistant. So in 1906, B&T figured this out. So if you look at different types of tissues and organs, how easily they're damaged by radiation depends on these factors. Radiosensitivity is directly proportional to mitotic activity, and it's inversely proportional to degree of differentiation.
Can you say that again?
Radiosensitivity is directly proportional to mitotic activity. So the higher the mitotic activity, the more sensitive. And it's inversely proportional to degree of differentiation. The higher the degree of differentiation, the less radiosensitive. So that's just a different way of saying the same thing that's on the slide. So what are some body tissues that are radiosensitive? In general, all blood cells are radiosensitive because blood cells replenish on a regular basis. The white blood cells have a lifespan of 3 to 5 days. The lymphocytes are a type of white blood cells. They are one of the most radiosensitive cells in the body. Epithelial tissues. The epithelial tissues are coverings and linings. So the stem cells of the skin are particularly sensitive. The intestinal crypt cells. Y'all remember hearing about the crypts of Lieberkühn, the cells in the small bowel? Those cells are constantly replenishing. So again, they have a high mitotic rate. They are very radiosensitive. The reproductive cells, and specifically the immature reproductive cells. Immature sperm, the spermatogonia, and the small lymphocytes are the two most radiosensitive cell types in the body. And then of course, the lens of the eye is also radiosensitive. So all of these are examples of cell types and tissue types that are easily damaged by radiation. You say, well, okay,
Which ones did you say were the most radiosensitive? The reproductive cells, and what's the second one?
Say that one more time, Ivy.
I said, which two did you mention were the most sensitive?
The spermatogonia, the two that are on the slide, the spermatogonia and the small lymphocytes are the two most radiosensitive cell types in the body. And oddly enough, mature eggs and mature sperm are relatively resistant to radiation. But when they are in those stem cell, those precursor cell stages, they are very sensitive. So if those are the sensitive tissues, then what are the resistant tissues? Well, the resistant tissues are those which are complex, okay, highly differentiated functional cells that do not divide or divide very seldom. So the top 3 tissues in the body that fit that criteria would be the nervous tissue, the muscle tissue, and the liver tissues, the liver cells. So these are tissues that can withstand a lot of radiation before they would be damaged. Okay, so don't forget, the first thing you look at is the sensitivity of the tissue that is being irradiated, and how sensitive it is. Always go back to the law of B and T. Look at mitotic rate and look at degree of differentiation of the cells.
Is it just coincidental that the resistant tissues is like the liver regenerates, the muscle can rebuild, the nervous tissue has that covering? Is it just coincidental that they have these things and that, or does that play a part?
I'm not sure I'm understanding exactly what you're asking, but the main characteristic is that they don't divide regularly. They
Not just,
generate,
I'm saying
they
like
don't
the
typically
liver.
have to, only at injury or only at, you know, say if somebody's liver, half of it was removed to transplant, the liver would then regenerate, but otherwise it's not going to.
Gotcha.
Divide very seldom. So their mitotic rate being very low or non-existent most of the time is what puts them into that radio-resistant category.
You answered it, thank you.
Okay, all right. So the next factor that influences the radiosensitivity of an organism is the oxygen effect, or what we would really just say as how much oxygen is present when the irradiation occurs. Studies have shown that tissue is more sensitive to radiation at higher oxygen levels. In the next unit, we'll talk about cell survival curves and experiments where they have irradiated cell populations at normal oxygen levels. Then they have decreased their oxygen levels just slightly, and then they have decreased the oxygen levels to they've just barely got enough oxygen to be alive, to keep the cell alive. And what those studies have shown is that the greater the amount of oxygen present, the more damage done by the radiation. And the reason for that is that oxygen, the presence of oxygen, enhances free radical damage. So if there's more oxygen in the system, it can join with those hydrogen free radicals and can produce hydroperoxyl free radicals. So it's almost like it causes sort of an avalanche effect with free radical production. And we know free radicals are responsible for the greatest amount of biological damage. So the greater the amount of oxygen, the greater the damage due to radiation because of enhanced free radical damage. So oxygen is good for healing as long as you make sure that, you know, you can go in the hyperbaric tank, but don't be irradiated while you're in there, because you would be much more sensitive. Okay, the third biological factor that we look at is age. And when we think about age, we can measure it two ways. We can measure it from birth to death, or we can look at it from conception to death. If you look at it more broadly, from the point of conception through the gestation period to birth, then all the way through the lifetime of the organism, studies have shown that organisms are most sensitive to radiation in the embryonic stage. And the embryonic stage is approximately the first trimester, or the first 3 months of a pregnancy. Well, think about what is happening in that time period. In the first trimester, you start off with a single cell. That cell then starts to rapidly divide. When it gets to the blastocyte stage, then it starts to differentiate. But early in a pregnancy, we have many very simple or poorly differentiated and rapidly dividing cells. So what does the law of B&T say about that?
More sensitive to radiation.
More sensitive to radiation. So again, in that embryonic stage, that is the most sensitive stage in the lifetime of any organism. Now, if you look from after birth, you consider birth as your starting point. If you look from birth to old age, sensitivity is greatest in the very young and the very old. If you look at a graph or a chart, it would start off very high at the young age, young children. It would drop, it would level out all through like most of adulthood. And then when you get to old age, sensitivity increases again. With children, think about how rapidly children grow. If children are in a growth stage for most of their childhood, then there's high metabolic activity. There's a lot of cell division. There's a lot of cell division. That means there's going to be increased radiosensitivity. And then you say, well, what about old people? Why are old people more sensitive? Well, there's different theories that say old people are not really more sensitive, but their repair mechanisms are breaking down because their tissues are older and they are degrading with time. That's just normal. So older adults are more sensitive to radiation because they may not have appropriate repair mechanisms that younger adults would have. It's also important to know that children and young adults are at an increased risk of cancer induction from radiation exposure when compared to other age groups. So again, sensitivity is greatest in the very young and the very old. In the young, because of more growth, metabolism increased, mitotic rate increased. In the very old, probably because of decreased repair mechanisms. Okay. Gender. How does gender influence radio sensitivity? Well, the results are really inconclusive because there's variability. Some studies have shown that girls are more sensitive in early childhood, that girls are at a greater risk of cancer induction from radiation exposure, particularly breast cancer, lung cancer, bladder cancer. Okay. Any exposure in girls younger than age 15 increases the risk of breast cancer. So that's one sort of group of research. Another says that with studies across lifespan, that males are overall more radiosensitive. So basically, we don't really know. There's differences. There's no conclusive research that says gender impacts, radiation exposure impacts one gender more than the other than I think it is generally agreed on that girls are more sensitive in early childhood. All right, so the next thing we look at in terms of biologic factors is increased temperature and metabolic rate. So if you have increased temperature and metabolic rate, a higher metabolic rate means more chemical activities going on in your body, more cell division. Well, what do we know about higher rates of cell division? That means increased radiosensitivity. Temperature is actually measuring molecular motion on the atomic level. So if you have, again, more going on at the molecular level, you would have increased radiosensitivity. All right, what about stress level? Are any of y'all stressed? It's still pretty early in the semester. Is anybody stressed? We're all stressed. It's a pandemic, right?
I was about to say, when are we not stressed?
When are we
right
not
now?
stressed these days? Exactly. And we wouldn't be as stressed if we were on campus in the classroom. Let's say that. So anyway, if you have increased levels of stress, that increases your metabolic rate. If you have increased metabolic rate, you have increased radiosensitivity. So I love this stress reduction kit here. Place this on a flat surface or a firm surface. Follow the directions. Just bang your head against the wall. So repeat it until you're unconscious. If you're unconscious, please stop the activity. Has nothing to do with radiosensitivity. I just thought it was funny.
Good one, Don. That was.
Y'all have to have a sense of humor. We have to laugh. That decreases our stress level and makes us more radio resistant.
And it makes our telomeres longer.
It does. Well, good. All right, body weight. Thinner organisms are more radiosensitive, and the reason is unclear. I said it's because if you have enough body fat, then the radiation can't penetrate to get to the vital organs, but that's just my theory.
It's mine too.
Yours too, so really. So here's the thing. If you want to be the most radio resistant, you should
Be fluffy.
You be fluffy, yeah. Well, you should have just enough oxygen to keep you alive. You should be somewhere in middle age. It doesn't really matter if you're male or female. You should have a low metabolic rate, a low body temperature, no stress, and just be a couch potato so that you gain weight. So all of those things would make you less radiosensitive. But instead of having to worry about dying from radiation exposure, you'd probably die of a heart attack. So, you know, something's going to get you one way or the other. So I think it's preferable just to be healthy and hope for the best. Don't worry about massive radiation exposure. We hope that's never likely to happen. But anyway, all of these things are biological factors. These are factors related to the organism. So now we're going to switch gears. We're going to switch gears and we're going to look at physical factors. And the physical factors are related to the radiation and how the radiation is administered. Now we're going to focus most of the time on LET and RBE, because a lot of these things toward the end are common sense, and you already know about them and how they relate to potential biological damage. So like I said, we'll spend most of our time on LET and RBE. So the first of the physical factors, LET. LET stands for linear energy transfer. And LET really is a description of how much energy is the radiation leaving in matter as it passes through. So if you could have a diagram of all the different energy that the radiation deposited as it moved through an organism, you could calculate LET. It is the rate of energy deposition. It is one method of expressing radiation quality, but it's not the method that we use in diagnostic radiology. When we're talking about the quality of the beam, what do we usually mention to express the quality of the beam?
Penetrability?
KVP.
KVP, which is that controls the penetrability. So in general diagnostic radiology, we're simply going to mention our KVP level to give us an idea of beam quality. But LET can be used to express beam quality in other situations. So since LET is the rate that energy is deposited as the radiation moves through the biological system, its units are in keV per micron. So how many kilo electron volts of energy is transferred per millionth of a meter of tissue? Because that's what a micron is. A micrometer is 1/1,000,000th of a meter. So again, linear energy transfer. How much energy is transferred as the radiation moves through the biological system? There's a term referred to as the particle track, and the particle track is simply the path of the radiation through the biological system or through a cell. So for example, here we have this line that simply indicates the particle track. So here we have a blue line for a low LET radiation. We have a red line for a high LET radiation. As the radiation moves through the organism, it is interacting via ionizations and excitations. The interactions may occur directly or indirectly, that doesn't matter. But every time we have an interaction, we have energy deposition. So we see in this example of the high LET radiation, there's a whole lot of interactions along this particle track in a relatively short distance. So if we are transferring a lot of energy over a short particle track length, that would indicate a high LET radiation. Here we have a much longer particle track, and then we see, well, we've got a few interactions here, we don't have any here, and then we've got a few more down here. That would indicate fewer interactions, fewer ionizations and excitations, less energy transferred along the particle track. So that would be descriptive of a low LET radiation. So a high LET radiation is transferring a lot of energy along the particle track. A low LET radiation is transferring little energy or less energy along the particle track. So what influences the LET of a radiation? And there are two things. One is particle charge. The other is particle velocity. So the LET of a radiation is directly proportional to the particle charge, and it's inversely proportional to the particle velocity. So the higher the charge and the slower it's moving, or the lower the velocity, the higher the LET. Okay, y'all get that?
Say that one more time. The last thing you just said.
Particle charge, the lower the velocity, the higher the LET, or the more energy it's going to transfer along the particle track. Then the opposite would be true. The less the particle charge.
So you said higher the
velocity.
particle charge, right?
I'm sorry? What, Marcus?
You had said higher the particle charge and on the first one, right?
The higher the particle charge and the lower the velocity, the higher the LET. And then
Okay.
lower the charge and the higher the velocity, the less LET. The less energy is going to transfer. So let's look at this diagram on this slide.
Is that just because it's moving faster through the cell?
Yep, yep. So let's look at these. Here's some different types of radiation. And we're just going to look at the first four types: alpha, beta, gamma, and X-rays. Alpha particles. What do alpha particles consist of? What are they?
It's
It's a helium nuclei, but what is that?
helium.
So what
Neutrons.
nuclei consist of?
Neutrons.
Neutrons and protons.
Neutrons and protons, two specifically. An alpha particle is 2 protons and 2 neutrons, which is identical to a helium nucleus, okay? In terms of particles, that's massive. Alpha particles are big. And since they have 2 protons, what is their relative charge?
Positive.
Positive how much?
Huh?
Positive how much? Put a number.
4.
Positive 2. They have 2 protons and 2 neutrons. Neutrons have no charge. Protons have a charge of +1. So alpha particles have a charge of +2. So that's relatively high. Then we have beta particles. Beta particles are identical to electrons. So if they are identical to electrons, what is their charge?
Negative.
Negative what?
1.
1.
Negative 1. Okay. So alpha particles have a charge of +2. Beta particles have a charge of -1. Doesn't matter if it's positive or negative, as long as it's charged. Okay. X and gamma rays are identical except for point of origin, so we'll look at them together. What's the charge on X and gamma rays?
No charge.
No charge. They are neutral. So in terms of LET and charge, which do you think would have the highest LET? Alpha, beta, gamma, or X-rays?
Alpha, because it has the highest number.
Has the highest charge. That's exactly right. Alpha particles out of these 4 types of radiation has the highest charge. Therefore, it is going to have the highest LET. Alpha particles can not only physically knock electrons out of orbit, they can attract electrons out of orbit because they have that charge of +2. Electrons would be attracted to that positive charge. So they can create ionizations both by direct collision and by attraction, electrostatic attraction. Beta particles have a charge of -1. They can create ionizations by direct collision and also by repelling electrons out of orbit. X and gamma, since they have no charge, can only interact with electrons and give them enough energy to escape the atom. So by direct collision, basically. So alpha particles having the highest charge would have the highest LET when we look at it from that perspective. All right, well, let's look at velocity. How fast do X and gamma rays move? How fast do they travel? Speed of light. So they're moving very quickly. Beta particles and alpha particles move much more slowly. So again, LET is directly proportional to particle charge and inversely proportional to particle velocity. The slower they're moving, the greater the likelihood of an interaction. So therefore, the higher the energy exchange. Because remember, linear energy transfer. It's all about interacting and transferring energy.
Can you say that one more time?
Which
Greater.
part? I'm making this up as I go, Courtney. I don't know what I said.
You said the slower the
The
movement.
slower the particle is moving, the more opportunities it has to interact with surrounding atoms and electrons. So the greater the likelihood of an interaction, and when we have interactions, we have energy exchange.
Got it.
You're welcome. Alpha particles that are large particles with a relatively high charge of +2 and moving slowly is more likely to interact, more likely to ionize and excite, more likely to transfer energy. So they have a higher LET value. X and gamma, which are moving at the speed of light, have no charge, are much less likely to interact. So they would have a lower LET value. One thing also that's important to know about LET, LET is not constant. The LET of a given radiation is sort of an average over the track length because all radiations interact like this diagram. So here we have the depth of tissue is here. The green line is the velocity. The red line is LET or ionizations, because as the number of ionizations go up, then the number of energy, the amount of energy transferred is going up. So LET is not constant. As the radiation moves through the system, it starts to lose velocity the greater the depth it goes into the tissue, the further it travels. When it's moving at a pretty good rate, LET is relatively constant. So it is interacting pretty evenly across the track length. But right before it comes to rest, we get to what's called the Bragg peak. The Bragg peak is sort of the last hurrah of the radiation, where it is getting rid of all of its energy. So you have a lot of ionizations just before it stops. So the Bragg peak is the point at which the energy exchange or the energy transfer is the greatest. And for particulate radiations, it occurs just before they stop. They're going very slow. And remember, LET is inversely proportional to velocity. Velocity is decreasing, then LET is increasing.
So would the Bragg peak be the top of the red line?
Yep, the Bragg peak, if I can get my, here we go. Yes, this is the Bragg peak. This is the peak of this red line. Because like I say, as the particle's moving pretty steadily, the ionization rate is steady, but right before it comes to rest, you see this massive increase. It's going very, very slow now. Slower it's going, the greater the likelihood of an interaction. An interaction results in energy transfer. So the Bragg peak is just this peak where energy transfer is the highest. So to summarize LET, this is just a summary of everything we've really said. High LET radiations are going to transfer a lot of energy into the biological system. And because of that, there is an increased risk of biological damage. So high LET radiations are characterized by high particle charge, low velocity, and many interactions along the track length. Low LET radiations are just the opposite. They have a low charge or no charge. They have a high velocity. They're moving quickly. They have few interactions along the track length. And therefore, less energy is deposited and there is decreased chance for biological damage. Just to give you an idea of some LET values, 250 keV X-rays, which is a little outside the diagnostic range. It would be like some of the low, very low therapy X-rays, have an LET of 3.0. So 250 kVp X-rays are transferring 3 keV of energy per micrometer. Now, if we look at electrons or beta particles, because beta particles and high-speed electrons are the same. If you had a 1 keV electron, so a very low energy electron, it would have an LET of 12.3 keV per micron. It has a higher charge, you would expect more energy transfer. Then we look at alpha particles. A 5 MeV alpha particle, which is much higher energy than X-rays, relatively speaking, has an LET of 100 keV per micron. So you don't have to memorize those numbers, but you do need to know, relatively speaking, alpha has the highest LET, beta or high-speed electrons would be next, X and gamma would be the lowest. And again, they have no charge, they're moving at the speed of light.
What was the example you gave for the beta?
Beta or electron, the high-speed electron had an LET value of 12.3 keV per micron.
And what was X-rays?
The X-rays were 3. So the 250 keV X-rays were 3 LET per micron. The 1 keV electron was 12.3 keV per micron. And the 5 MeV alpha particles were 100 keV per micron. So the alpha particles are transferring much more energy into the tissues and therefore would be causing increased biological damage. Does that make sense? Is that good?
Yes,
Yes, sir.
thank you.
All right. Okay, so now we look at the second of the physical factors, and this is RBE. And RBE stands for relative biological effectiveness. And RBE is on page, let's see, 766 in the Carroll text. And it is on page 120 in the Statquist Shearer text. So if something is on a relative scale, what does that mean? As we talk about relative charge, we talk about relative mass. Now we're talking about relative biological effectiveness. So
Is it gonna like the standard, like almost like a relative?
we are comparing it to a standard. So we're comparing it to something else, okay? So relative biological effectiveness compares the effectiveness of different types of radiation in producing a given biological effect. And it's comparing the effectiveness of that radiation to 250 keV X-rays. So 250 keV X-rays are the standard. And if I were going to do an experiment to determine RBE for a given radiation, you have to pick a specific endpoint to measure. So for example, I might want to compare the effectiveness of alpha particles at producing skin erythema to 250 keV X-rays at producing skin erythema. So I would have to run my experiment to see what dose it takes and then make the comparison. Once you have done your experiment, RBE is calculated by dividing the dose of the standard radiation, and our standard radiation is the 250 keV X-rays, to the dose of the test radiation to produce the same biological effect. So when that says a specific biological endpoint, what it's talking about is a biological effect. Is it skin reddening? Is it cataracts? Is it leukemia? Now, these experiments are done with laboratory animals. So you might see an experiment that looked at the effectiveness of alpha particles to produce leukemia in laboratory animals as compared to the effectiveness of 250 keV X-rays. But it's a relative scale, so we are always comparing it to our standard.
But it's always about it producing like an incident, like a bad thing, or?
Yes, a specific biological effect. Radiation generally does not produce good things. You'll find out all those movies are wrong. You know? But yes, I mean, and like I said, it could be, the endpoint would depend on the researcher. It could be hair loss, it could be erythema, it could be leukemia, it could be skin necrosis. I mean, whatever endpoint they wanted to study. But the point is, it's always compared to that standard 250 kVp X-rays. It's important to note that RBE is directly related to LET. The high LET radiations are imparting more energy, so they're going to do more biological damage, and they will have high RBE values. But remember that LET was not constant, so RBE values are also not constant. They can vary slightly with the LET as the LET of the radiation varies, and they can vary with biological endpoint. So for example, if you calculated the RBE for alpha particles to produce skin erythema, you might get an RBE value of 20. What does that really tell you? What does that tell you if my RBE for alpha particles at producing skin erythema is 20? Any ideas?
The fact, is it the fact that it has, never mind, I don't know.
You don't know? Well, I mean, at least you're willing to give it a shot.
It's low LETs.
What, Marcus?
Is it low LETs?
Nope, it's not
Gonna
going to
be
be low
high?
LET.
It's gonna be high LETs, right?
Yeah, alpha's high LET and high RBE.
Right.
RBE value is telling you. So for example, if I did an experiment and I said it takes 250 rads, or that would be 2.5 gray, to create erythema using X-rays, the 250 keV X-rays. So it takes 2.5 gray, an absorbed dose of 2.5 gray, to produce erythema with the X-rays. But it only takes 0.125 gray of the alpha particles. So the RBE would be 2.5 divided by 0.125, and that gives me an RBE of 20 for alpha particles producing erythema. So it took 20 times less dose of alpha particles to produce erythema. So what that means is basically is that alpha particles 20 times more damaging than X-rays to the skin. Okay, so the RBE value is telling you how much more damaging that radiation is when compared to X-rays to produce that biological effect. So what would it mean if I did an experiment comparing gamma rays to X-rays to produce erythema, and my RBE, after my experiment was done, I calculated my RBE and it equaled 1. What does that mean?
They're the same.
They're the same. Gamma rays are equally damaging to X-rays.
Anything times 1 is the same. It's just whatever you're
Yes, if it's on a relative scale, if they're both 1, they're both the same. Exactly. And then what if I did an experiment and I came up with that for radiation Z, whatever kind it is, its RBE was 0.75. Or
It's
less than
0.75 times.
So would it be more damaging than X-rays or less damaging than X-rays?
Less.
Less.
Less. So remember, this is a relative scale.
Less.
So we're comparing the damaging ability of radiations to 250 kVp X-rays. If we come up with a number that's higher than 1, that means they're more damaging than X-rays to produce that specific biological endpoint. If we come up with a comparison and their RBE equals 1, they're equally damaging to X-rays. If we come up with an RBE less than 1, that means they're less damaging.
So is X-rays RBE always 1, or you're just using that as an example?
No, it's always 1 because it has been set as the standard.
Okay.
It's the standard of comparison. It's always 1. But again, RBE values can vary slightly. So we said we got an RBE value of 20 for alpha particles to produce erythema. If you did an experiment with alpha particles to look at hair loss or epilation, the RBE might not be exactly 20. It might be 18 or it might be 21. They will generally be in the ballpark, but they're not exactly constant. They're not constant across all biological endpoints or effects, whatever it is you're measuring. And so here's sort of an example of that shows you how RBE and LET are related. For diagnostic X-rays, they're right in the range of 1. Okay, so LET and RBE. But we notice as LET is increasing, RBE is also increasing, with alpha being at the top. And cobalt 60 and X-rays are down here toward the bottom end. They're low LET, low RBE values. Neutrons, fast neutrons are, we're seeing an increase. And then with alpha, that's the highest. So they are directly related. LET and RBE are directly related. High LET values will have high RBE values. All right. So the next of the physical factors related to biological damage is the time of delivery. How are we giving the radiation dose? Is it delivered acutely, which means all at once, an immediate exposure? Or is the dose fractionated or protracted, which means it's given over time? So for example, if we take an exposure, any X-ray that we take, general diagnostic, that's an acute exposure. The radiation is delivered instantaneously. In radiation therapy, they can't deliver the entire dose at one time. It would kill the patient. So they break the total dose up into fractions, and they give equal fractions over time. Protraction is the same thing. We'll talk, well, it's a little bit different, but we'll talk more about exactly what it is in just a minute. But you must know this. If you want to have the greatest biological effect, you give the dose acutely, all at once, because that will cause the most biological damage, because the patient will not have any time to repair. So fractionation. Fractionation is not something that we deal with in diagnostic radiology. Fractionation is something that you will see in radiation therapy. And if any of you choose electives in radiation therapy, you will note that they are giving very large doses. For example, 4,000 rads, or that would be 40 gray, or 3,000 rads, or 30 gray, large doses, which if you gave them all at once would kill the patient. So they break the dose up into equal fractions, and they give the dose and exactly the same dose rate over time until the total dose is administered. So for example, if you had a patient who was having radiation therapy and they needed a total dose to their tumor of 3,000 rads. If you gave them 3,000 rads at once, it's going to kill them. So we don't want to kill the patient. So we say, okay, we can break this dose up. We can give them 100 rads per minute, give them a 1-minute treatment per day over 30 days. If we do that, we should kill the cancer cells. Cancer cells are poorly differentiated and highly mitotic. So B and T tells us that cancer cells will be more sensitive to radiation. But by waiting 24 hours between doses, the normal cells have time to repair. So this is fractionation. When you take a total dose, break it up into equal fractions, deliver it at the same dose rate every day over a long time period. And so therefore, the patient can survive the total dose, but hopefully the total dose will kill all of the cancer cells and not kill the patient, which is very important. Now, there are some types of therapy, radiation therapy, that use a protracted dose, and these are pretty rare. They are used sometimes to wipe out a patient's bone marrow when they need a bone marrow transplant. But a protracted dose has a total dose that is delivered continuously, but at a very low dose rate. So for example, and this is unrealistic for a patient, this could be done with laboratory animals in research. For example, if you wanted to deliver a dose of 500 rads, you could deliver it at a very low dose rate, say 2 rads per hour, over 250 hours continuously. Protraction is just like fractionation. When the dose rate is very low, the body is still able to repair itself. So, in terms of the greatest biological effects, the greatest biological effects occur when the total dose is delivered acutely, all at once, an immediate exposure. Fractionation and protraction are techniques that deliver the dose over time so that the patient is not killed by the total dose, but hopefully the cancer cells can be killed. All right, the next of the physical factors is probably the most important factor related to biological effects, and that is how much radiation is delivered. What is the total dose? So when we talk about the quantity of radiation, we're talking about the total dose that the patient receives. Common sense, you know this, says that the higher the quantity of radiation, the greater the degree of biological damage. So if we look at this chart, and this chart is in rem, which is an old traditional unit, it's not in sievert. You could convert it to sievert by dividing it by 100. So at doses of up to 25 rem, which would be 0.25 sievert, there really are no effects or very few effects of radiation that can be affected. When you get to doses between 25 and 100 rem, or 0.25 and 1 sievert, we can now measure decreases in blood cell count. So you might have first decreased white cell count, then decreased red cell count. When you get above doses of 100 rem, between 100 and 200 rem, or that's 1 to 2 sievert, you start getting into what's called the NVD syndrome. So it's nausea, vomiting, diarrhea, and again, you're still seeing decreases in blood cell count. When you get to 200 to 300 rem, or 2 to 3 sievert, you have vomiting, diarrhea, anorexia, which is loss of appetite, and the patient starts to feel lethargic. So you're losing energy. 300 to 600, you're getting more of the same, it's getting worse, and you start to get damage to the gastrointestinal system, and some patients will die in this dose range. If you are above 600 rem or 6 sievert, pretty much everybody dies. So common sense tells us radiation is harmful. The higher the quantity of radiation received, the more severe the biological effects. And we will come back to this chart and the different effects when we get to the unit on the acute radiation syndromes. But higher the quantity, higher the damage. Now, the second of the physical factors is the quality of the radiation. Now, the quality of the radiation in diagnostic radiology is determined by KVP. That's what we talk about. So the range is 40 to 150 KVP. In the diagnostic energy range, the higher the KVP and the higher the quality of the beam, the more penetrating the radiation. So it's less likely to be absorbed, which means we would have decreased biological effects. So in the diagnostic energy range, a higher quality beam is less damaging. Why do you think we have in every procedures and technique class pushed high KVP, low mass technique? Mass is quantity, KVP is quality. We want a high quality, low quantity beam, and that will best protect the patient, causing fewer biological effects. The last of the physical factors affecting biological damage is field size or field of view. Obviously, the larger the field of view, the more body tissue is irradiated and the greater the dose. In general diagnostic radiology, we should never be doing total body exposures. We should be concentrating on a specific body area. That body area is determined by the procedure that's ordered. You always need to select the smallest possible field of view that will demonstrate the necessary anatomy. This is one of the things where I think we are falling down on as a profession, not just y'all, not just me, all of us, because one of the things that I've seen over the last 10 years is increased fields of view, decreasing collimation, a decrease in proper collimation. We know that some technologists may crop the images, and that's totally unethical and should never be done. We don't want to have to do it that way. We want to be able to position it properly, center properly. If we're centered properly, then we can have an appropriate field of view. But we want to minimize field of view to just the anatomical area of interest. Therefore, we are irradiating less body tissues. So the physical factors that impact biological effects. High LET radiations will transfer more energy to the biological system and will cause more biological effects. High LET radiations typically are also high RBE radiations. They're more effective at producing biological damage. In terms of time, the greatest biological effects are seen when the dose is delivered acutely. Fractionation and protraction allow time for the body to heal and to repair. The most important physical factor in determining the effects of radiation is the quantity of radiation. Higher the quantity of radiation, greater the biological effects. In terms of radiation quality, in the general diagnostic energy range, the higher the quality of the radiation, the greater the penetrability of the beam, the fewer biological effects that will be seen. So again, high KVP, low mass, technical factors. Field size or field of view, you should limit the field of view to the anatomical area of interest to minimize biological effects. So when we think about all the different factors that influence the biological damage to an organism, some are related to the organism itself. Some are related to the radiation. All of these things together impact how an organism will respond and the type of biological effects that will be seen. So, any questions? Any short one-liners? Anybody have a journey? No.
Now I'm going to say that if I picked up a pound, that I'm actually making myself less radiosensitive.
Just keep saying that. I said it for years. Didn't see much impact. So any questions, any comments?
And I was gonna say, like with the field of view part, like most places, they rather you leave it open so you don't have to go back and repeat. So like I had a lumbar spine and I'm at EP Hawks and she said, leave it open. And I was gonna call me and she's like, no, leave it open. And it was a good thing I left it open because the patient has scoliosis.
Mm-hmm.
So you don't really know.
And there are cases like that, but I would say don't leave the field of view open to account for your sloppiness. Yes, on that one patient, it made a difference. But what if you did 50 other lumbar spines and none of them had scoliosis and the field of view is still wide open? So, and there have been change in department protocols because when I first came into the field, we did all lumbar spine on 10 by 12 image receptors. So that was our field of view. We had a film at the time. Now, what are you doing them on? 14 bys. That's a lot more body tissue. And if you're not collimating on a 14 by, yeah, that's a lot more exposure. So sometimes it's important, but if we can center and position appropriately, we should be able to use the smallest possible field of view. And again, you are working in departments, so you have to go by their protocol. So I understand that. So don't be sloppy, be good, do your exams appropriately, and hopefully we can use the smallest field of view. But I know that you're right. Lumbar spines particularly, they use a large field of view. And that's kind of bad because where are the female reproductive organs? Right beside the lumbar spine. Any other questions? Okay, well, you have test 2.
And they got rid of shielding.
Yes, yeah, we'll talk about shielding at later points. So test 2 will open tomorrow at 4. It's due by end of day Saturday, so on the 26th.
Sunday?
If when you are reviewing, you have questions, let me know. I will happy to either do a Zoom call or just send me an email if you have any questions.
You didn't say Sunday for the test, no?
How
Saturday.
come we do Saturdays and not Sundays anymore?
because you have other tests that are probably all due on Sunday, where we're trying to flex it a little bit. Do you have any other tests this weekend?
MR does
Yes.
on Sunday.
Not to put them off all until the last day. Let's see.
I'm good.